Section 3.2, Measures of Spread. First, we'll talk about the range. The range of the data set is the difference between the largest value and the smallest value. So as an example, the average monthly temperatures in degrees Fahrenheit for San Francisco are listed. So if you want to find the range, you take the 63, which is the biggest number, and subtract 51, and you get a range of 12. Although the range is very easy to compute, it's not often used in practice. The reason is that the range involves only two variables from the data set, the largest and the smallest. When the data set has a small amount of spread, like the San Francisco temperatures, most of the values will be close to the mean. When a data set has a larger amount of spread, more of the data values will be far from the mean. The variance is a measure of how far the values in a data set are from the mean on the average. The variance is computed slightly differently for populations and samples, and the population variance is presented first. So again, we have all our numbers, x1, x2, and however many they are, denote the values in a population of size n. So if there's 5 numbers, 4 numbers, that's what the n means. Let mu denote the population mean. So this is the first formula, population variance, and it's read sigma squared is equal to the sum of xi minus mu squared divided by n. So, for instance, if we're looking at the example with population variance, I want to compute the population variance here. The first thing I need to do is compute the mean. The reason I need the mean is because the mean is in the formula right here. So, to calculate the mean, I add up all the numbers and divide by how many there are. So I add 51 plus 54 plus 55, 56, 58. I add those all up, and that comes to 690. And then there's 12 of them, so I divide by 12, and I get a mean of 57.5. The next thing I'm going to do is for each population value, I'm going to subtract. So I'm going to take each value and subtract the mean. So for instance, notice how all of these numbers are listed on the chart, the same as they are here. But on this step here, right below it, I'm taking the number, which would be 51, and I'm subtracting the mean, which is 57.5. So 51 minus 57.5, if I take it on my calculator, and I do 51 minus 57.5, I get minus 6.5. So that's this number here. Then I do it for the next one. 54, so I go 54 minus 57.5, press the equal button, and I get minus 3.5, so that goes here. So all of these numbers are subtracted and placed after the subtraction. This is what happens with the values. So then I go to the next step. Step 3, square the deviations to obtain x minus mu squared. So if I look back at the original formula, which is here, right now what I did was I took xi and I subtracted the mean. That was the last step. Now I'm going to take that number that I just subtracted, but I'm going to square it. That's what the next part says, square it. So if I go back to the data now, right here, this negative 6.5, negative 3.5, these are the numbers that I subtracted. So now I'm just going to square. So I'm going to take minus 6.5 and square it. So on my calculator, I can do negative 6.5 times a negative 6.5, and I get 42.25. Another way I could do it is use this x squared button. You have an x squared button on your calculator, so you could do parentheses, negative 6.5, close the parentheses and square it, and you get 42.5. The reason you have to put parentheses around it is because you want to make sure that the negative gets squared. Another way you could do it is just realizing that anytime you square a number, it will always be positive. So all of these numbers, you're just basically multiplying them by themselves. So negative 3.5 times negative 3.5, that's going to give you a positive 12.25. Every single one of these is squared. All right, so the next thing they do is add them up. So why are they adding them up? Let's go back to our original formula, and that is found right here, the summation. It says add up all those numbers that you just squared. So I go back and notice the 42.25, that's the first one I squared, 12.25, second one, 6.25. So I go through this whole blue list here, add them all up, and I get 169. Finally, the next thing to do, again, this sigma squared is the variance, and this is population, is to divide by how many there are. So you add them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 items, so I divide by 12, so I get 14.083. When the data values come from a sample rather than a population, the variance is called the sample variance. The procedure for computing the sample variance is a bit different from the one used to compute a population. In the formula, the mean is replaced by the sample. So again, we have different symbols. That's no longer mu, it's now sample, but it's still a mean. And also, this is changed. It's not s squared, or it's not sigma squared. And the last thing that's different is you're not subtracting by n, you're subtracting by n minus 1. So if there's 12 items, you would divide it by 11. So instead of dividing by 12, you would divide by 11. So why do we divide by n minus 1? Well, when computing the sample variance, we use the sample mean to compute the deviations. For the population variance, we use the population mean for the deviations. It turns out that the deviations using the sample mean tend to be a bit smaller than the deviations using the population mean. If we were to divide by n when computing a sample variance, the value would tend to be a bit smaller than the population variance. It can be shown mathematically that the appropriate correction is to divide the sum by the squared deviations by n minus 1 rather than n. So when you're doing a sample, you just divide by n minus 1. So here's an example of a sample variance. A company that manufactures batteries is testing a new type of battery designed for laptop computers. They measure the lifetimes in hours of 6 batteries, and the results are as follows. So 3 hours, 4 hours, 6 hours, 5 hours, 4 hours, 2 hours. Find the sample variance of the lifetimes. So the first thing you have to do is find the mean. Again, they don't tell you to find the mean. You just have to remember you have to find the mean. So you add them all up, and there's 6 of them, so you divide by 6, so the mean is a 4. The next thing you're going to do is do the subtraction. So it's 3 minus 4, 3 minus 4, 4 minus 4, 6 minus 4, 5 minus 4, 4 minus 4, 2 minus 4. Those are all the subtractions. Then they square them. Again, they're running it through as just one step instead of the 3 other steps. And finally, instead of dividing by 6, you divide by 5, and you get the sample variance is a 2. So again, let's take a look at this. If I did 3 minus 4, that would be 1. Now I square 1, that's a 1. I do 4 minus 4, that's a 0. 0 squared is 0. 6 minus 4, that's a 2. 2 squared is a 4. 5 minus 4, that's a 1. 1 squared is a 1. 4 minus 4, that's a 0. 0 squared is a 0. And finally, 2 minus 4, that's a negative 2. Negative 2 squared is a 4. So you add this up, 4, 5, 6, 7, 8, 9, 10. That gives you the 10 divided by 5. Because the variance is computed using squared deviations, the units of the variance are the squared units of data. For example, in the battery lifetime example, the units of the data are hours and the units of variance are squared hours. In most situations, it's better to use the measure of spread that has the same unit as the data. We do this simply by taking the square root of the variance. This quantity is called the standard deviation. The standard deviation of a sample is denoted by S, and the standard deviation of a population is denoted by sigma. So the standard deviation of a sample is the square root of S squared. Of the population, standard deviation is the square root of sigma squared. Now remember, the S squared was the variance of a sample, and sigma squared is the variance of a population. So on the other example with the sigma squared, to get the 14.083, you need to take the square root of that. So to take the square root of the 14.083, I would do 14.083. This is the square root button, so I have to put that in first. Depending upon what kind of calculator you have, you either put it in first or second. So 14.083. Usually if you can see the symbol when you press it, that means you put it first. If you press the button and you don't see anything, that means you put the number in first. So square root of 14.083, I get 3.752, and they get 3.75. They rounded it right there, so this is a 7, so that rounds up to a 3. And then finally, the square root of 2 on the other one that they got. So again, second function, square root of 2, and rounding it to 3 places, 1.414. That's what I get for that. And then they have some computer steps. You can look that over. And recall that a statistic is resistant if its value is not affected by the extreme values, large or small, in the data set, but the standard deviation is not resistant, so that means it is affected by extreme values. Bell-shaped histogram curves. I'm going to stop the video here, and I'll make another one and start up right at this point.